Okay, thanks. Let me start by thanking the organizers for the opportunity of giving this talk. And in the following, I'm going to present a recent work I've done in collaboration with David Andriot and David Erkinger in Vienna. And the topic of this talk will be the so-called swampland program, which is an intense topic of research in the stream community at present. So okay, sorry. So I will start by giving an introduction, and then I will, at the end of the talk, I will present briefly the results we obtained in this context. So the central question in the swampland program is the following. Can all consistent effective theories be coupled to gravity in the high energy regime, so in the ultraviolet? This is a yes/no question. So if you answer yes, you mean that then gravity is not really constraining the form of the low energy effective theory. While on the contrary, if you answer no, the situation is a bit more interesting because this means that gravity is constraining the form of your low energy effective theory. And let me just remind that effective theories are the best tool we have at present to understand physics, theoretically at least. The crucial point now is that string theory, and in this talk, I will always assume that string theory is the description, the consistent description of quantum gravity, then string theory says no. So this means that in string theory, not every possible effective theory is a good effective theory. And to give you an example of what I mean, I will start with this simple idea. It is strongly believed that in string theory, there are no global symmetries. So this is a conjecture in the sense that we don't have a general proof, but also we don't have a counterexample. Recently, there has been a step forward in proving this statement, and thanks to Arlo and Auguri, we know that this statement is true under assumptions. So in specific setups, we are able to prove this. In particular, Arlo and Auguri used one of the most important results, which is the so-called ADS-CFT correspondence. This is a duality between a theory of gravity, of quantum gravity, in an anti-de Sitter space, which is a space with negative vacuum energy, and a conformal field theory. So they were not able to prove the statement about the non-existence of global symmetries in quantum gravity, so on the ADS side, but they were able to prove it in the conformal field theory side. Then the question arises whether we can go beyond this. So a first step would be to prove this generically, so to turn the conjecture into a theorem. And also another question would be whether this fact that there are no global symmetries is somehow the unique thing we can understand about quantum gravity at present, or if there are other properties, for example, other restrictions.
Just a question.
Yes.
What did they add to the knowledge of the 80s? It was already known in the 80s that string theory has no global symmetry.
Well, as far as I know, there is no rigorous proof of this.
Well, perturbatively, yes. It is based on CFT.
Okay, but what I know is that they were able to prove this. I mean, ADS-CFT is a non-perturbative also statement. So they were able to prove this also in the full quantum gravity, let's say, using the dual CFT, as far as I know.
Okay, thanks.
So, so if you accept, okay, if you accept the idea then that not everything goes in string theory, in quantum gravity, then you can set up the following program, the so-called swampland program, which aims to distinguish effective theories which can be coupled to quantum gravity in the UV from those which cannot. So what I'm saying is that the set of all consistent effective theories is in fact much larger than the set of consistent effective theories, which in addition can be coupled to gravity. So those which can be coupled to gravity are said to be in the landscape, which is the green region I'm drawing here, while those which cannot be coupled to gravity are said to be in the swampland, from which the name swampland program. Now, the best strategy one could imagine, one can imagine to study this subject would be really to start from string theory and then to just compute the form of the possible effective theories. So to derive really from string theory everything. However, at present, this is not feasible because we don't have a complete understanding of string theory. So the best we can do, and the strategy which the community is trying to follow now, is the following. First of all, you collect some known examples from string theory of constructions which are believed to be consistent in string theory, and then you try to guess some general properties out of these examples. And then, secondly, you try to turn this guess into a conjecture, so a sharp statement about some property that you believe to be true in string theory. And these conjectures, of course, have to be tested. So this means that there should be almost no known counterexample to this statement. So what I'm saying is that we are not really able to draw where the landscape and the swampland are, so to draw the border between the two. But with conjectures, we are trying to exclude part of what we think is the swampland. Now, this is not satisfactory, as you can, of course, think, but at least the presence of conjecture means that we have some work, lot of work in front to be done and things to understand. But most importantly, in my view, the presence of conjecture is telling us where to look first in the investigation. So string theory is a vast and a huge framework, which we don't understand completely. And hopefully conjectures are telling us where new results and new concepts can hide. However, as I will show in the few slides, at present we have just a set of conjecture and the picture is not very clear. So the first thing you would like to make things clearer is to try to relate conjectures to one another. And this also should be a consequence of the idea that string theory and quantum gravity are somehow unique. So all these statements should be related if they are correct. And in particular, for this talk, what I will try to do is that when some of this conjecture will involve parameters, then we would like to say something very precise about these parameters and not that they are just order one numbers. So you would like to put, for example, bounds on the parameters. So this will be essentially the last part of the talk. Now, let me give you an overview of the swampland program. As I was saying, our present understanding of the swampland program is some list of conjectures that we have. Some of them are very robust. For example, the fact that there are no global symmetries, or the fact that gravity should be the weakest force, the so-called weak gravity conjectures. However, some other are not so solid. In this talk, I will concentrate only on 3 of them, and I will first review them, and then I will show which results we have obtained. So we'll concentrate on the last 3 conjectures I'm showing here, essentially because all of these involves parameters, and all of these have sharp statements in the sense that there is one formula I can check in actual computation. So we'll start by reviewing the no de Sitter conjecture. This conjecture is quite recent, 2 years ago, but it immediately gained a lot of attention in the community. Essentially, if you want, the statement is that in quantum gravity there should be no de Sitter vacuum. And the formula they proposed, the authors proposed, is the one I'm showing here. So any scalar potential in a consistent effective theory, of which can be coupled to quantum gravity, should satisfy this bound. So we have the gradient of the scalar potential the modulus of the gradient should be bigger than the actual value of the scalar potential, where we have an order 1 parameter C, which is not specified by the authors, and this will be the subject of the later part of the talk. The motivation for this is not really physical, but as far as I know, this conjecture was proposed only because there is no clear, neat example of a de Sitter vacuum from string theory. The best proposals we have are KKLT and large volume scenarios, but these involves ingredients which are not really completely understood, for example, non-perturbative effects. And for this reason, there is no common agreement in the community, in the string community, about the general validity of this construction. However, what we do know is that in certain corners of string theory, so again, under assumptions, we are able to prove that this conjecture is actually true. So there cannot be de Sitter vacua. But there is no general proof for the whole string theory. It is why it is a conjecture. And as I was saying, here we have a parameter. So this is why I'm reviewing this conjecture in this talk, because we can calculate this number here in string frame, the string compactifications. Now, the second conjecture is more recent, and is so-called the Transplackian censorship conjecture. And the idea of this conjecture is that sub-Planckian quantum fluctuation should always remain quantum and should never cross the Hubble horizon and then freeze and become classical. So this is the original statement. There has been also recently a criticism about this, but what is important for this talk is not really this bound they proposed, but a consequence of this bound. So when you take this, the idea of the conjecture and you apply it to a system with the scalar fields and a scalar potential, then you can derive a bound on the form of the scalar potential again. And this is already in the original paper. So you see that this formula here in the end of the slide is quite similar to the previous one of the no de Sitter conjecture, with two main differences. Here, first of all, there is this average, which means that they are integrating over an initial value of the scalar field phi and the final value, and then they are dividing by the field displacement delta phi, and eventually they are sending delta phi to infinity, because otherwise on the right-hand side you start having terms, corrections, which goes like 1 over delta phi, so you want to suppress these corrections. The second difference is that there is not really a parameter here, but there is a precise number which depends on the space-time dimension. So if you set it equal 4, which is the space-time dimensions we observe, then you have precisely this number, square root of 2 over 3. The last conjecture I'm going to review is less recent and also a bit more abstract. This is the so-called distance conjecture. And the idea is the following. So when you have an effective theory with a certain number of scalars, you can think of these scalars as coordinate of some field space, some internal space. Then you can calculate the distance in this field space, like you usually calculate distances. But most importantly, you can ask your theory, your effective theory, what happens when you look at infinite distance in this field space. So if you want in the asymptotic region or the boundary of this field space. Then this conjecture is telling that this should not be allowed. So you should not look at infinite distance into this field space, because otherwise an infinite number of exponentially massless fields start appearing to your theory. And then since you have an infinite number of new light degrees of freedom, you have to completely reformulate your effective theory, or if you want, the original effective theory breaks down. And the mass of these new fields has an exponentially suppressed behavior, which goes with the distance, which is sent to infinity, and then there is again a parameter lambda, which is not specified in the conjecture. Again, this conjecture, I'm reviewing this conjecture in this talk because we know in certain setups how to calculate the parameter lambda, and this calculation will mostly use supersymmetry, in fact. Now, going into the last part, I will show now how it is possible in certain setups to calculate these parameters, and we'll try to see if there are some relationship which seems to arise from this calculation. So let's start from the no de Sitter conjecture. A good framework in which to calculate, to test this conjecture, is 10-dimensional supergravity. So 10-dimensional supergravity is the low energy effective theory of string theory, so is a good framework in which to perform calculations in general. However, as long as you are in 10 dimensions, there is no scalar potential, and so there is almost no room to prove to test the no de Sitter conjecture. However, a scalar potential is known that arises when you compactify your theory. So even if 10-dimensional supergravity and string theory live in 10 or 11 dimensions, then what we observe are 4 dimensions. So we always would like to restrict our attention to 4 dimensions. So you assume that the other additional dimensions are compact, and then you can just do this dimensional reduction. And in general, a non-trivial scalar potential, depending on many scalar fields, will arise. In the work I've done in collaboration with the group in Vienna, we calculated the scalar potential from type 2 supergravity and looking at 3 particular scalar fields which were already studied in the literature before. So we calculated this explicit form of the scalar potential, and every time we were able to recast the scalar potential into an inequality of this type here, where A and B are numbers which we calculate explicitly, so are known coefficients we have. And importantly, for arriving at this step, we had to use assumptions. Otherwise, the right-hand side would not vanish. So once you are here, you can recognize that this is very similar. In fact, it's almost the same equation, inequality predicted by the no de Sitter conjecture. In fact, once you are here, you can immediately read off the parameter C, which is this combination of the parameters A and B.
Excuse me, what is rho, tau, and sigma?
Are 3 scalar fields which are usually arise in string compactification. So rho is associated to the volume of the internal manifold. This is a scalar which is telling me how big is the internal manifold, the typical size of the internal manifold. Tau is related to the so-called axiodilaton, is related to the dilaton of string theory, and sigma is another field. Okay, this is not always arising. So in my internal manifold, I'm assuming to have 2 sub-manifolds along which I'm putting sources. And this sigma is somehow parameterizing the ratio of these 2 sub-manifolds. But rho and tau at least are called universal scalar fields because they are believed to arise in most of these compactifications.
Sorry, I also have a question you're
Yes.
partially mentioning, already answered. Which kind of manifolds do you consider? Which compactifications are you?
We are doing compactification on nil manifolds here.
Okay, thanks. Yeah.
Okay. So we can calculate then this parameter C, and what we have done, we calculated the parameter C in 10 different examples, just because we used 10 different assumptions to set to 0 the right-hand side. And in all of these examples, we were obtaining a value of C, which was actually bounded from below exactly by the bound predicted by the TCC. So we have these 2 conjectures, which are similar in form, but they are not really related a priori, and still we seem to find some relationship. So this supports the idea that conjectures should be at least related. Now let's come to the last conjecture. In the distance conjecture, there is a parameter lambda, and as I was saying, a good framework in which to calculate this parameter lambda are theories with n equal to 2 supersymmetry, which comes from string theory compactification on Calabi-Yau manifold, so a different internal manifold with respect to the one I considered in the previous setups. In particular, we know how to calculate lambda for certain states, for BPS states and Kaluza-Klein states. I will not enter the details of this, it's just to mention which kind of states we know how to calculate. And then we collected, first of all, 19 known results, which I think are most of if not all, the known values of lambda, which have been calculated, and we calculate also 3 new ones. So we have a set of 22 values of lambda, and all of them again satisfied a bound. And what was surprising to us is that this bound is not completely unrelated to the previous one, but actually is again, there is again this factor of square root of 2/3, which appears with a factor 1/2 now. And this was confirmed later on independently in this work, which used some black hole arguments, also relating this to the weak gravity conjecture. Now, before concluding, so what I showed is that we have these two parameters, C and lambda, which a priori are completely unrelated. So they are they belong to different conjectures. And a priori, there should be any order 1 number, generic order 1 number. However, what we do find, calculating them explicitly in controlled setups, is that there seems to be a relationship among these parameters, and at least they seems to be bounded. And the bound we found is the one I'm showing you here. So they are bounded by some lower value, lambda 0 and C0, where lambda 0 and C0 are related by this simple relation, which has which shows also the connection with the Transplackian censorship idea. So motivated by this, we tried to propose some possible correspondence between conjecture, but it's very speculative. Anyway, what we are saying is that every time in a setup the distance conjecture is satisfied by some mass m, then there should exist a dual setup in which the de Sitter conjecture is satisfied by some scalar potential v. So to conclude, the motivation of the swampland program is to understand property of quantum gravity in string theory. However, since we don't have a complete understanding of string theory, the tool the community are using at present are conjectures. And then if you want to simplify the picture, there is a good starting point to find the relationship among conjectures. So in this sense, we found evidence that some of these conjectures should be related, and we also put bounds in the associated parameters. But the main open questions which remain, and which is still, in fact, is the central question, is why this seems to happen. So what is the physical principle underlying the fact that these parameters are bounded? And for example, is the TCC idea the physical reason underlying the no de Sitter conjecture? So thanks for your attention.
Can I ask a question?
Yes.
This is Matteo Bertolini. Hi.
Hi.
Am I allowed to make questions? I'm asking the host, the chairman. Hello.
Sure, go ahead.
Okay. So can you go back to slide number 15, please?
Yes.
So just a question. Here you have considered a bunch of a bunch of concrete models in which you computed C, and then you said that they all satisfy this bound.
Exactly.
How near were you able to go to square root of 2/3?
In some cases, actually, this is saturated. So in some cases, we find exactly square root of 2/3.
Okay.
I don't remember now how many, but at least 2 or 3 of them, I think they are saturated.
Okay, thank you.
Can I ask a question?
Yes.
You know, the line of thought that you have followed have the criticism of the descendant at infinitum. Namely, you can provide the millions of examples.
Yes.
But you never know if the millions plus one will defeat your thesis. So what
Yes.
I want to say is, do you have any more way of arguing, I mean, more solid way of arguing than just providing examples?
Well, I personally don't have. As far as I know, I think this is this logic is the one which is followed now in the community, because I mean to prove this generally you should really understand completely string theory. I think which is I think we don't. No, now. So I don't think there is at present another feasible way other than this. I think this is why this swampland program is being investigated a lot.
But has been ever found any counterexample so far? I mean,
no, this is the point. In all the conjectures which are taken seriously, there is no counterexample known. Or if you want, no universally acknowledged counterexample. So the De Sitter conjecture, we have KKLT, which is a construction and well-studied construction, but the community is not totally agreeing on the fact that the construction is completely consistent and under control.
Okay, thank you.
Thanks.